like to welcome you to the March meeting of the Experimental Aviation, Chapter 88, Wichita, Kansas. Looks like we've got a pretty good turnout, and this should be a pretty good meeting tonight. It's about 9 years ago I wrote an article to one of the first issues of the Experimenter magazine. I wrote about my Wren Ultralight, and at the time what I was writing about was the possibility of forming a new racing class, and at the time I was going to call that racing class Formula R. And the whole idea of the Formula R racing class was to increase the reliabilities of the two-stroke ultralight engines. They've come a long way in the last 9 or 10 years, but as you'll hear from Mike, they're not completely there yet. But the whole purpose was to come up with an airplane very similar to this AR-5. And when I saw the AR-5, I said, there's my Formula R racer. Well, what I think would be a really neat thing, I don't know, I'm not saying we're going to do this, but I would love to see a class of airplane built around this very airplane and using roughly the same specifications of this airplane. About 10 years ago, Steve Wood taught me that for every pound of engine weight you can eliminate, you can take 3 pounds of weight total away from the airframe. And when you chase your tail like this and you take the weight away, you start reducing external volume and area, you start going faster and faster and faster. And when you reach the end of that design cycle, you end up with something like the AR-5. And it's my pleasure to introduce Mike Arnold, the current record holder of the C1AO world record at 213.17 mile an hour. Mike, take it over.
Thank you very much. We really haven't discussed too much about this Formula R thing here, but that's a very nice thought. Thanks, Mark, very much. And thank you all very much for inviting me here. This has just been a thrill for me. I'm a country boy from a little town in Northern California, and here we are in Wichita. Jeez. Ed Hooper was kind enough to take us through and show us the Starship today. What a deal for a composite guy to see. Thanks, Ed. And thanks, Mark, for getting this great idea for inviting us over here. What we're going to try to do, we have 3 hours of film that we've completed on this airplane, and we don't have time, obviously, to show you all. But what we're going to do is show you what we think you might like to see for 20 minutes or so, just skipping through the process. And then we're going to open it up and ask you folks, I'm going to read a menu to you basically and ask you folks what you'd like to see. So, Max, I'd like to introduce my friend Max too. This is Max Volume, musician by trade and very excellent. Max has been helping me for years. We've done all kinds of crazy projects together. Max has, you'll get a chance to hear Max in action. He's a master guitar player. You'll hear him on the film. And without further ado, let's just start out with the intro, Max, at 1 minute and 20 seconds.
Okay, if we could do away with these lights
Yes,
right here.
if you folks will do us a favor and just shut those 2 switches off. That switch. Incidentally, you're going to see some of the stuff that's never been seen before this afternoon or tonight, so.
This one, here we go.
This is Mike Arnold's AR-5. It's 14.5 feet from the tip of the spinner to the tail, and a little over 21 feet from wingtip to wingtip. It's mostly made of fiberglass and epoxy over styrofoam. The airplane was made entirely without molds. The engine is a completely stock 582 Rotax 2-cylinder liquid-cooled 2-stroke with a gearbox. When it's working right, it puts out about 65 horsepower. In August of 1992, Mike surprised the experts by setting a new 3-kilometer world speed record for airplanes weighing less than 661 pounds gross. (213.18 miles per hour).
That's our little intro, folks. I need to talk to you a little about, before we go any further, about what really inspired me to do this. I built an airplane that some of you may know, or I worked on an airplane that some of you may be familiar with, called the Amsoil Rutan Racer. It was a biplane, tandem wing airplane. Okay, I see heads nodding. I didn't design it or anything, so. I happened to be out at Reno crewing on that airplane in '82 when B.J. Holmes came out and sprayed it with asenaphthene to determine how much laminar flow we were getting on those wings. And I saw with my own eyes that we were getting laminar flow back to 60% of the chord, which was fairly remarkable. B.J. Holmes was impressed. Having worked on the airplane then, when it came time for me in that same year to design the AR-5, I was confident that I could get the same kind of long laminar runs that they were getting on the Amsoil Racer, and basically it inspired me to do it. We're going to get right into another one here. That'll be 30-30.
30-30.
So what we also saw was that we were getting laminar flow behind the propeller. Some of you may know about this already. It's been traditionally felt that you couldn't get laminar flow behind the prop, or at least there wasn't going to be enough of it to make it worth your while. But the B.J. Holmes study was very clear that came out as a result of these natural laminar flow experiments, that you could get intermittent laminar flow behind the propeller at least, if not constant. So that really encouraged me to go ahead and use long laminar run airfoils on the AR-5, and that's basically, we'll talk about it some more, but that's basically why the airplane goes so fast. So, I can see where we are here. Not quite up to 30-30. Well, I'm talking about, we also used laminar run airfoils not only on the main wing, but on the tail surfaces as well. They're Wortman sailplane profiles. I might as well tell you now that the wing is an old NACA 65 series 418, 18% thick at the root, and 15% at the tips already. Go.
Then I'd have problems seeing out, of course. So, okay, and that pretty much takes care of the fuselage. Let's take a look at the wing. This is the first thing you notice about this wing is that it's very thick. It's a 65 old NACA profile, 65 series. It's a 418 at the root, going on out to a 215 at the tip. The reason I made the tip airfoil have less camber than the root was that I was trying to simulate the span-wise lift distribution of a more tapered wing. You'll notice that this wing is not very tapered, and I did that for a couple of reasons. The first is that if I reduced the taper on the wing, I got to make it shorter in here toward the root, toward the fuselage. That helped me do a little trick that I'll talk to you about later in terms of interference drag reduction. The wing is also a very high aspect ratio for a sport plane. It's an 8-to-1 aspect ratio. That helps in terms of reducing the interference drag at high angles of attack in climb or in takeoff. It allowed me basically to use this little two-stroke engine, which has a very low power band, a very narrow power band, and very low torque at low RPM. So where you really suffer with a little engine like that is trying to take off and climb. So high aspect ratio helps in that very much. The wing is a thick wing. It's 18% thick because I was looking for stiffness and lightweight. If I made the wing thinner, it would be, I'd have to put a lot more material in it to make it as stiff as a wing that's thicker. So that thickness is good for the structure structural considerations, but it's bad for speed. So I could make the airplane go faster by making a thinner wing. The wing is also quite large. The area is 56 square feet. That's to keep the stall speed down, to make the airplane handle well at low speeds, and of course I can make the airplane much faster if I made that wing area smaller as well. Didn't do either one of those things. The wing is a laminar flow wing, what they call laminar flow. All wings, incidentally, are laminar flow back to a certain point. What airfoils that are called laminar flow are really just extending the laminar flow back a little farther than it would be on a normal airfoil. The wing surface is fairly smooth, and nothing really remarkable about the surface.
Wait a minute, that's not quite true. I hadn't checked it with a wave gauge yet. Wave gauge is a neat little instrument. It's just an old-fashioned dial indicator mounted to an aluminum block with 3 little legs sticking down. It's set up so that by moving it along the wing surface, you can detect even the most minute little bumps and dips. It's very accurate. This particular one belongs to Bruce Carmichael. He's used it a lot on sailplanes. I don't believe I've ever seen one used on a power plane before. Smoothness is so important on sailplane wings because they use the same kind of long laminar run airfoils I've used on this airplane, and these airfoils just don't work if they're not smooth.
Okay, that's got it. Oh, this is very good.
Is it?
Yeah.
Oh, look!
Now, what you have to remember is that we have expanded the vertical scale here. Let's see now, this is 10 units here is an inch, and 10 units here is 2/1000ths of an inch. So we're exaggerating it 500 times. The vertical scale is exaggerated compared to the horizontal scale.
Can we put that down here, Bruce, so we can take a look?
Now I'm going to draw some mean lines through, and we'll look at peak to peak, and
So that is an exaggerated chart
Yeah.
showing the
That's
waviness.
500 times lumpier than the wing?
yeah, right.
500 times lumpier
Yeah.
than the wing actually
Yeah.
is. Yeah.
Now, where we see this biggest joggle through here is in your spar location, and that's where it's hardest to keep the...
Just about where I'd
because you have-
expect it.
Yeah. Now, if we look at peak to peak, see, we've got this much is 1/1000th of an inch.
Mm-hmm.
500's the bad.
So we're coming up here peak to peak. We've got 1, 2, 3, about 3 3/4 peak to peak wave at that point.
3 3/4 thousandths.
Yeah, and this one is 1, 2, is 3 3/1000ths peak to peak. That means that put a mean line through, you've got about 1.5 parts in 1,000 ripple in the wing, which is what the racing sailplane pilots work all winter to get their wing waviness down somewhere close to this.
Really?
But most of them will quit rubbing when they are peak to peak 4/1000ths of an inch
And this is
or
peak
more.
to peak.
This is peak to peak 3 here at this point, and that is very, very low waviness. I've seen our experimental shops at Rockwell work weeks to build a research model for a wind tunnel or a water tunnel and reduce the waviness to this order. Somehow you did it in your home workshop.
Boy, I got lucky.
Well, it wasn't so much luck. I sanded on it for 3 solid months.
What the B.J. Holmes study indicated was that this Reynolds number, which the Reynolds number I operate at speed is about 5 million. He said that basically you could expect to get the kind of laminar flow performance that I got, even though you had peak to peak 10/1000ths of an inch. So basically I overdid it. Doesn't hurt, but you don't have to do that. So I'm sorry, I just told you some wrong information. It's 20/1000ths you can get away with peak to peak at Reynolds number of around 5 million. So you can do that according to the B.J. Holmes study, as long as you don't stack up these waves. You can get away with 1 or 2 waves at 20/1000ths, as long as you don't have them one right after the other. So I don't know what else to tell you about that, except it works. You really do get laminar flow. The next thing we want to look at is we did some other things too. We didn't just, we were concentrating here on the wing because it's the main influence on this high speed. So run up to 3803 if you would, Max. We did the normal stuff. We made the airplane smooth. That's just anybody who has done anything with composites. This incidentally uses the same sort of composite techniques that Burt Rutan uses on his very easy and long easy airplanes. These airplanes are built basically by laying fiberglass over foam, so you're working from the inside out rather than as you do on a molded airplane, working from the outside in. So the surface that you develop on an airplane like this is pretty much dependent on how much sanding you want to do, or how much, not only how much sanding, but how much microfill you want to put on the airplane. I figured, and I mentioned this in the article in Sport Aviation, that I have about 30 pounds of painted filler on this airplane. So for a small airplane, that's a lot. But you pretty much have to do it if you want to get laminar flow. We did all the other, we did a lot of other little things that we'll talk to you about later, but one of the things that I like is interference drag. That's what we're going to show you now.
The airplane wouldn't be stable. All of this brings me now to the point where we can talk about one of my favorite subjects, interference drag. That's something that occurs right down in the wing root here. What I thought I knew about interference drag when I started this whole thing was that it was something that happened in the corners of things, something that happened right down in where two sides met. Like, for example, these two sides here. I understood it to be something that happened with the boundary layers from the two surfaces getting mixed up in the corners and sort of beating themselves up and wearing themselves out, so that somewhere downstream here they would separate or transition from laminar to turbulent flow earlier than they should. I thought that until I read an article by Mr. Raymond Parker in one of the aircraft design manuals that the EAA Association puts out. Mr. Parker was talking about interference drag reduction in a way that I had never heard before. Take a look at this. Mr. Parker worked with Gus Raspet at the Mississippi State University. They are a very famous program there, and they were working on sailplanes. This is an airplane built by Mr. Parker, and they modified the airplane by changing the top of the fuselage here and by moving the canopy around and doing all kinds of other stuff. But you notice there's no fillet in there. They're not talking about the kind of interference drag that I knew about. Take a look at this other picture over here. This is what the airplane looked like when it was finished. You can see that they put a little bubble canopy up on top, and they cut the whole top of the fuselage down over the top of the wing. And they also made the fuselage thicker back toward the trailing edge of the wing. I didn't know what in the world they were talking about. I knew it was important stuff because they say it's the most often made mistake in aircraft design. That is something that you do wrong at the wing root. And I also had heard stories from Irv Culver about an airplane that he had worked on that had such bad wing root interference drag that the airplane wouldn't get off the ground until Irv came along and made a special fairing for it. But I didn't know how to make that fairing. I didn't understand the theory. What kind of interference drag is this? I spent a lot of time trying to answer that question by looking through Horner. One of the things he talks about are what happens when you put a couple of struts like these in the wind tunnel. These happen to be off the landing gear struts on the AR-5, and they also happen to be about 5 chord lengths long, each one of them. Total of 10 chord lengths if we put the two of them together like this. Remember that because we'll talk about that in a little bit. Horner says that if you put one of these things in the wind tunnel and measure the amount of drag, let's just arbitrarily say it's about a pound of drag on one of these. The other one you stick in a wind tunnel, it'll be about a pound. And if you stick them then both in the wind tunnel, you should get a total of 2 pounds of drag. Well, that works until you start to move them a little closer together. When you get them about this close together, the drag is starting to go up considerably. Not just 2 pounds, but something like 3 or 4 pounds. When you get them close enough together so that they're about a half of a width apart, the drag triples. 6 pounds of drag instead of 2 pounds of drag. Now what in the world is going on there? Let's take a look at the blackboard and see if we can figure it out. What Horner says is going on, here are the 2 struts here. Horner looks right in this area right here. And what he notices is that what we have here is a sort of diffuser. These 2 sides are getting wider as they come out toward the bottom. And Horner notes that as the 2 struts move closer together, let me draw this side here as if we've moved them in closer together, that the expansion ratio, that is the distance between here and here compared to here and here, gets greater as the strut moves closer. Let's see what that looks like. We've got one length here, we've got about that length down here, another one down here. It looks like about an expansion ratio of 2.5. When we move the strut in this close, we have this distance here, 1, 2, 3. Sure enough, the expansion ratio here is about 3.5 to 1, and here it's about 2.5 to 1. Now, what he also notes is that as the expansion ratio in this thing that he calls a nozzle, you see that? You see the nozzle in there? That's what we've got, a nozzle. That as the expansion ratio in this nozzle becomes greater, the drag goes up. Well, very interesting. What could you do to fix that? Well, one of the things that occurs to me that you could do is make one of these sides straight. That would sort of reduce that expansion ratio. There it's 2 to 1. Well, yeah, how would you do that? Bring this side in there, bring this side. We're not making a biplane here anyway, so we really don't care about that. But keep that in mind. We're going to talk about something else now. Okay, here are these 2 little struts again, the 1 pound drag struts. And in this little experiment, Horner puts the 2 struts together to form a T, and puts the whole unit in the wind tunnel, and discovers that the drag, just by putting these 2 things together, has doubled. It's now, instead of 2 pounds, it's 4 pounds. So that means that something down here in this intersection is causing as much drag as the 2 struts themselves. Now what's going on? Horner, by this time in the book, has stopped referring to nozzles, but I see a nozzle right back here. Can you see that? Right back from the point of maximum thickness on the airfoil here, back to the trailing edge, it expands just like that nozzle. As a matter of fact, if you look at it from the side here, you can see that it's expanding in 2 directions. This side's falling off as well as this side. So it's expanding in both directions. It's not a fully bound nozzle, it's not a round circle, but it's 1/2 of that circle that's creating that nozzle. Well, what can we do then to reduce that drag caused by putting these 2 things together? Horner shows us how to reduce it down to 1/10 of its original value. Okay, I've drawn this on the chalkboard. This, of course, is this, and these 2 lines are represented by these 2. What Horner does is he fills in the area behind the point of maximum thickness on the airfoil here. He fills in the nozzle with a fairing that looks like this. And because he gets out that far, he has to put an after body on it. So he does something that looks like this. All of this area in the nozzle is filled in. Interesting, isn't it? Just about what you'd do at a wing root fairing with a properly designed fairing, filling in the funnel. Okay, let's take a look at something else. This is really interesting. I love this one. Here's Horner again, and here's a little study that I have reproduced on the blackboard magically over here. In this study, they put a streamlined body in the tunnel. This is a body of revolution, it's round, and they put a wing on it. And they looked to see what position fore and aft produced the most interference drag. When they started with the wing way up here, the drag was low. When they moved the wing back, the drag got higher, back, the drag even higher, back, even higher, and right about here, the drag peaked about 4 times as much as it was up here. And then when they moved it back, it got a little less and a little less and a little less until finally back here it was back down to a reasonably small value. The reason everybody knows that when you put a wing on the after part of a fuselage that the interference drag is low is basically because the boundary layer gets very thick back here. Interference drag is not a problem in the back. So when you put a horizontal stabilizer or a vertical stabilizer on an airplane, you don't have to worry too much about interference drag. But right in here, which is pretty close to where you want to put a wing on a normal airplane, the drag is very high. What's going on? The only way I can see that, Horner doesn't talk about this, but the only way I could figure it out was to arrange the drawing so I was looking at it from the top. Here's that wing, nice tapered wing, and if I make a line here that represents the airstream going past that wing, I see immediately a nozzle. Look at that. Here's the thick point of the wing, and from here back it's opening up like mad. There's the drag. So what can we do to fix that? Well, we could put a little fairing in here like this, like we did on the 2 struts, or we can do what I did on the AR-5. We can make the fuselage sides straight, eliminating that nozzle. You have a little bit of a problem here trying to get the fuselage streamlined back down, but it seems to work. So that's it. Big deal. Okay, so here's the straight line. We ran it right from, in this case, right from the vent here, which turns out to be the same width as the fuselage back here. So we ran the straight line right from the vent all the way back to this point right here. While I was filling out the nozzle, I also made a Horner style fairing in here, increasing the radius from the point of maximum thickness on the wing all the way back to the trailing edge. And I also positioned the canopy so that it was filling out this nozzle area all the way back to where it peaks here at the trailing edge. You'll notice that the point where I let everything go here is not all the way back to the trailing edge. The trailing edge is a couple of inches farther back. What I did was I let it all go when the top of this laminar flow wing started to return. It has a little cusp up here, so as soon as it started to curve back up, I let all this stuff go. One more thing, I mentioned earlier that making the chord of the wing shorter helped me to do all this stuff. If the wing had been a much longer chord here, I would have had to carry all of this straight line way back here. So short chord helps. Also, I want to talk to you a little bit about this piece of masking tape here, which represents the exhaust streak. I spent some time looking at exhaust streaks on other airplanes. For example, the P-51. You can see that it goes way up over the point of maximum thickness on the wing and drops way down toward the trailing edge. And you can see that also on the Yak-9. It is also set up about the same way the P-51 is. Both these airplanes have their maximum widths right over the thickest point of the wing. So they have nozzles. The Focke-Wulf 190 is probably the worst example. You can see that the point of maximum thickness on that fuselage is well forward of the wing, and it's tapering throughout the whole distance from the leading edge to the trailing edge, and you can see the exhaust is being pulled well down into the fairing toward the trailing edge. On this airplane, you can see that the exhaust streak is quite high. None of this high peak over the point of maximum thickness, and that, I'm sure, is a result of this business we've done here in the wing root. Okay, let's take a look a little further aft here, and you can see what's happened as a result of reducing this downwash angle as we have. Now it's up here on regular low-wing airplanes. It would be down something like this. It's affected the trim on the airplane in a negative way, as far as I'm concerned. I had spent a lot of time trying to set the incidence on this horizontal stabilizer, and was disappointed to see when I first flew the airplane that the elevator was riding like this. I needed a little more incidence than I have. And of course, as far as I'm concerned, that's a result of having changed this downwash angle here. So obviously what we did at the wing root intersection is having some effect, good in some ways and negative in other ways. That pretty much takes care of interference drag. Let's finish looking at the rest of the airplane. The last thing that all of the experts wanted to talk about that they thought helped reduce the drag of the airplane is the landing gear strut. The first thing they noticed was that it was outboard of the propeller wash. That means that high velocity air coming from the back of the propeller is not striking the landing gear. The other thing they noticed was that we knew how to make good Horner style fairings. We filled in the nozzle back here. It's a little difficult to show you the whole gear right here in the shop because we've had that little mishap. Let's take a look at some shots that we took out in the field. The strut airfoils themselves have a length to thickness ratio of 3:1. Horner says that's just about optimum. And they intersect the wheel pant at the edge of the pant, which eliminates an inside drag-producing corner. The wheel pant itself also has a fineness ratio of about 3:1, and it fits as close to the tire as I thought I could get away with without it rubbing. It's a telescoping spring gear. The pant moves up and down the strut with the wheel. This little scoop provides cockpit air. Can you tell I like P-51s? Altogether, it's a pretty clean airplane. I tried to keep it as smooth on the bottom as it is on the top. You, in our talks, you have pointed out to me that the airplane goes fast, not because of any one thing. It goes fast because of a lot of little things that you've pointed out. Would you mind pointing those out again?
Okay. Yeah, I think first of all, because of your experience in composites, you were able to have the nerve to build a very fast composite airplane. And it's the smoothness that you get with the composite construction that is almost impossible to do in metal that allows you to capitalize on the best of the aerodynamic research on subsonic airplanes that has been done, principally on the wing, getting extensive laminar flow. And you picked a 65 series airfoil. It's been around since World War II, but it's a darn good low drag airfoil. And it has about half the drag of more conventional airfoils if it's smooth enough to actually obtain this low friction laminar flow from the leading edge back to about 50% of chord or further. And we saw with the weight measurements that you are far smoother than you would actually have to have been to, at these speeds, this size of wing, get laminar flow back that far. So you're very likely getting, if you had no control surfaces, you'd probably be getting drag every bit as low as those refined wind tunnel models that NASA ran in the low turbulence wind tunnel and got these drags that were half of conventional values. Okay, now, in putting on the control surfaces, again, from your experience with the sailplane people, you found out very clever ways to reduce any little drag increment from the fact that you have to have an active control surface there. Very close fit at the hinge line on all of your controls, your flaps, your ailerons, your elevator, your rudder. So that has been handled very well too. Then you were extremely concerned about the possible drag increment due to the interference between the wing and the fuselage, as we were talking about earlier. You were showing Horner's book on interference drag, what he has to say about it there. And you did all the right things there. The most significant thing you did was to keep the fuselage cross-section constant width back to the trailing edge of the wing, so that you weren't getting a slowdown of the air on the fuselage, adding to the slowdown of the air on the back part of the wing, and making for problems in the wing intersection. Now this is most important at high lift coefficient in the climb and between there and CL max, but you have to consider it a little bit too, even at the high speed point. In addition, you didn't just bring the wing in and butt it up against the fuselage. Now that's a nice right angle corner, which some of the textbooks say, hey, that's great. But what happens when you have two intersecting plates, or a wing and a fuselage, with an absolutely square corner, is the boundary layer on the wing and the boundary layer on the vertical wall of the fuselage get sucked toward each other into this intersection, and you get a very thick boundary layer buildup, which then is more prone to separating in that adverse pressure gradient at the back end. So your radius in here helps. And this radius of the leading edge softens the deceleration of the air into the stagnation line and gives you a better start on life as we come through here. And then on the back of the intersection, by building that out, you are able to also keep this contraction that this gives a severe slowdown of the flow and the possibility for separation, and then very cleanly handled at the back end of it there too. Now the thing that really impressed me when I saw the picture in Sport Aviation was, my God, the thing has got a fixed landing gear. But you did that, the very best that can be done with a fixed landing gear. Number one, you moved it outboard of the propeller slipstream, so it's only seeing free stream dynamic pressure, not goosed up by the propeller slipstream. And furthermore, those very clean struts, which are probably minimum drag struts that you could do within this geometry, are flying at zero angle of attack, because they're not getting swirling flow off the prop and inducing an angle of attack and running their drag off the minimum drag point. Your wheel pants are absolutely minimum frontal area pants, but with good radiuses. So again, it's probably a darn good compromise. Now I don't know how much wheel was hanging down below, but probably not more than 2 inches, maybe less than that, 1.5 inches. Yeah, in my calculations I assume 2 inches. So the wheel is very well streamlined off. So you aren't paying a big drag penalty for that. The canopy is very clean lines. I'll fill it again to soften that stagnation region into the start of the canopy, keeping the boundary layer thin, going up over the canopy, and the fuselage in back, even though you started later to taper it, plenty long enough. It's amazing what you can get away on a three-dimensional body in the way of necking it in compared to a two-dimensional wing, and still not have flow separation. So this, and you've done a pretty good job of minimizing the surface area of the airplane. All these things added together, I think, have done it. Now, the thing I didn't know much about until you showed me the plane today was the internal arrangements on the cooling flow. Mm-hmm. And I would think that that you have had to pay a similar drag penalty, maybe halfway between production light planes that don't do hardly anything to reduce that drag, and the very best that can be done with a liquid-cooled engine, like the P-51. Mm-hmm. So there's a room, I think, place within your geometry, I think, that could be improved.
And that you think we could fix by turning that radiator around?
Yeah.
You think, or
yeah.
maybe making one large radiator over here,
mm-hmm.
and
yeah, have fewer 90-degree turns in this flow through here, and also, if you can, within the geometry, do a better job of diffusing the inlet flow through a gradually expanding tunnel to try to get the speed down very low at the radiator face, so that you've converted the dynamic pressure due to velocity into the static pressure at the face of the radiator. So now we've got high pressure on that face of the radiator. We've got low pressure here with this beautiful outlet that you've designed, and will really take the air through there and allow you maybe even to reduce the size of both the inlet and the
You're going to make this
exit.
airplane go faster.
Oh yeah, I think it's extremely good, and you've done the most important thing already.
Now, would you like to ask some questions?
On your cooling,
Sure.
did you do any pressure drop measurements?
None at all. We just took a wild guess. I sized the inlet and the outlet. Let's see, you haven't seen that. It's hard for me to remember what you've seen here already. I've seen this movie so many times. We designed the cooling inlet, the cooling system, around a spinner that filled up the hole, the big hole in the front, down to about 0.6 inches all the way around the annular inlet. And we sized the outlet using a little formula. I wish I could remember what it was, but it's about 23 square inches total outlet and about 18 square inches, or it was 18 square inches before we pulled that spinner out of there. And that's all we did. We hoped for the best. So one of the things that Bruce and I are going to try to do next year, or through this year when we get the airplane flying again, is go through that cooling system again. We are going to do some delta T, delta P calculations on it. So we'll see what happens. One of the other things that we would like to do is test the airplane with the front blocked off. In other words, eliminate any internal flow to see exactly what sort of efficiency we're getting in that cooling system. But this is stuff that we want to do. We haven't done it yet. I can't answer any more technically than that. So we want to, yes, sir.
Can you speak some more about what you've done to get laminar flow behind the propeller?
Well, we do in the movie. I wish I could. Oh, well, why don't we just do that? Let me show you one more thing before. If you'll hold off on that question, we'll just go find that piece and show you. Basically, what we did is just make the shape have a favorable pressure gradient. In other words, it's expanding as far as we could get it to go. I don't think we're getting any laminar flow behind the firewall. I'm sure that we're tripping the flow when we get to the aft end of the cowl. That gap is enough to trip the laminar flow. So the only laminar flow I think we're getting is from the inlet lip back to the firewall. I'm just, sir. Across which? Well, yeah, you may be getting too technical for me here. It increases at the point of maximum thickness on a streamlined body. It's going faster than free stream flow. Yeah, prop wash is faster than free stream air for sure. But I can't quantify that. If it's okay, sir? No gap seals anywhere on the airplane. Just didn't get around to doing it. Oh, sure. Bruce Carmichael says that because we're down to about a 32nd of an inch gap on all those surfaces, that we're not getting a lot of flow. But we are going to work on the ends of the control surfaces to try to put some. I can't remember what the sailplane guys call that, but it's a little gap seal on the ends of the ailerons, the ends of the control surfaces. I'm just dying to show you what happened to the airplane here. So we had a little mishap. We want to show you.